Okay.
This conference will
So
now be recorded.
in the previous class, we were discussing things with respect to the timers. We started with the configuration of the timers. So we started generating a large time of 1 second with respect to the timer zero module. First, initially, we wrote a program which is used to generate a time of 1 second. We tried toggling LED for every 1 second, but we didn't use any scaling concept there because we had no idea of what exactly is the pre-scaling available or whether there is a post-scaling available. We had no idea, which is why we did not choose the concept of scaling. So without scaling, we tried generating a time of 1 second. Then after that, once we opened the data sheet of the PIC microcontroller, we found that the microcontroller has three timers associated to it. There is timer 0 module, timer 1 module, and timer 2 module. So to start with, we went with timer 0 module. So looking at the data sheet, we found that timer 0 module's resolution is 8-bit, where you can store a maximum of 255 value. It supports pre-scaling and it is going to raise an interrupt after there is an overflow from 255 to 0. So we looked into the program. The program was very similar to what we wrote here for the 1 second times generation. The only difference was whatever this timer register we found. So the name of the timer register was TMR0. The name of the interrupt flag was TMR0IF, and there was an interrupt enable bit also called as TMR0IE. And after that, we found like for the initialization of the timer, we have to look at some of the registers. So especially it's the option register with respect to the timer. So we saw how option register is actually configured. Then after this, we also saw how to configure timer 0 along with a pre-scale of 1:16. So if I use the scale of 1:16, to this scale, I had to replace it with 16. And we found that when scale is taken as 1:16, the count value turns out to be 1250. So that was 1250. So you keep visiting the ISR, and once you complete visiting the ISR for 1250 times, there will be 1 second of time achieved, and you are going to toggle the LED. Along with that, we also configured the timer 2 module. The special functionality or the special feature of timer 2 module is you have a special register called PR2 register, which is called as the period register, which is again of 8 bits, and it can store a maximum of 255. Now what happens is when you go with the PR2 register value, so you are going to like have some value return into the PR2 register. By default, there will be 255 return. So if you start the timer 2 module, it starts ticking from 0 and it reaches till the value whatever is returned to the PR2 register. Once that value is reached, there will be an overflow made to 0 back in the timer register. So whenever I want an interrupt to get generated just after 250 ticks, the only thing I'm supposed to do is I just have to write PR2 with the value 250. Now once the timer 2 register starts ticking from 0, 0 to 1, 1 to 2, 2 to 3, the moment it reaches the value which is available in the PR2 register, that is 250, so there will be an interrupt occurring. You can see between the timer 2 register and the PR2 register, there is a comparator which is going to compare the values between the two registers. Now, if comparison is made and both of them are equal, there will be an interrupt arise. So that is what we saw with respect to the timer 2 module in the previous class. So in fact, we configured timer 2 module with a pre-scale of 1:16. If you want, you can choose a post scale of rate varying from 1:1 to 1:16. The corresponding values have to be loaded to the timer register. So that is with respect to the T2 con register. So that was the configuration of timer 0 module and timer 2 module. Have you got any doubts here? Any doubts in this? Okay. All right. So let us continue with one small like program left in the timer 2 module. That is, if you see the features of timer 2 module, please understand, sorry, if you see the features of timer 0 module, we read something like, in case of timer 0, you can configure timer 0 as a timer. Also, you can configure the timer 0 as a counter. Okay, so I can configure timer 0 as a timer, or I can configure timer 0 as a counter. Now, if I'm configuring timer 0 as a timer, what am I going to make use of for every tick to happen? So what should I make use of for every tick to happen? In case of timer 0 configured as a timer. Come on. What will it use for the tick to happen if timer 0 is configured as a timer? Will it use an internal clock or an external clock? Yes. So that is going to make use of an internal clock. If you have configured timer as a timer, if you are configuring timer 0 as a timer, you are going to make use of an internal clock in order to make a tick happen. So you want a tick from 0 to 1 to happen, 1 to 2 to happen, 2 to 3 to happen. It all depends on the internal clock, that is your instruction cycle time. But there are possibilities that you can depend on an external clock. Okay, that is when you are making timer 0 as a counter. So you can configure timer 0 as a counter as well, but you are going to make use of an external clock. Now, external clock means, if you can see here, there is a point which says counter mode is selected by setting the bit T0CS. So T0CS is the fifth bit of the option register. So that is how you read. It is the fifth bit of the option register. So you are going to select the counter mode by setting the T0CS bit. But if you see the T0CS bit here, so T0CS is the one which is, okay, T0CS is the one which is used to select the clock. If you write it with 1, then you are going to make use of external clock. If you write it with 0, you are going to make use of an internal clock. So previously what we configured was timer as a timer. So I wrote T0CS with the value 0. This time I want to configure timer as a counter. So I have to set the T0CS bit. That means I have to write T0CS with the value 1. And one more thing what it says is, in the counter mode, timer 0 will increment either on every rising or falling edge of the pin RA4. So if you consider this register, that is the timer register. So previously, if you have configured timer as a timer, the tick from 0 to 1, 1 to 2, 2 to 3, 3 to 4, every tick was dependent on instruction cycle time, which is nothing but the quantum. But this time, if you want a tick to happen from 0 to 1, then if you want a tick to happen from 1 to 2, when you have configured timer as a counter, that is possible either at the rising edge or falling edge of the RA4 pin of your microcontroller. Okay, so ticking is going to happen depending on either the rising edge or the falling edge, which occurs at the RA4 pin of the microcontroller. Now let us observe and see which peripheral is connected to the RA4 pin of your microcontroller. Now please look at this. I am taking you to the PiximLab board. So here is your PiximLab board. Do you see any peripheral which is connected to the RA4 pin of your microcontroller? Please observe and check. Do you see any peripheral which is connected to RA4 pin of the microcontroller? Any visible peripheral which is connected to RA4 pin of the microcontroller? RA5 is there, but do you see any RA4? No, right? Okay. Now, we actually can have a separate peripheral connected at RA4 pin of your microcontroller. So as of now, if you observe, there is no peripheral which is connected to the RA4 pin. But what this data sheet says is, there will be a tick happening only if there is a rising edge or falling edge appearing at the RA4 pin of the microcontroller. So I have to make sure either there is a rising edge or a falling edge appearing at the RA4 pin of the microcontroller. But I don't have any peripheral connected to the RA4 pin of the microcontroller. So let me take a peripheral. You can go to the modules and click on spare parts. So if you want some other peripheral other than the one which is already available on the board, so you can go to the modules and click on the spare parts. Okay. So once you click on the spare parts, you will get a screen like this. Okay. Once you click on the spare parts, you are going to get a screen like this. Now you have options like inputs. You can choose the peripherals which are used to give the inputs. If you want, you can choose a peripheral which you want to get the output. So this time, I actually want to provide an input at the RA4 pin of the microcontroller. So I am going to select a push button. Okay. So I'm going to select a push button. Now there is a small bug here. The moment you select the push button, that will not appear here on the screen. So you may have to click somewhere in the middle of the screen and you will be able to see some push buttons available on the screen right now. Now if you see, every push button you see has something called NC written. And NC represents no connection. So none of the push buttons here have been connected to any of the pins. So NC here is no connection available. Now if I want one of the push button to get connected to the RA4 pin of your microcontroller, so I'm going to right click and click on the properties. So here the pin 1, you can select RA4 pin. Okay, so pin 1, you can select RA4 pin and click on OK. Now when you do that, there will be a push button that is RA4 pin, there is a push button which has been connected to the RA4 pin of the microcontroller. Are you able to observe this? Okay. Now, after I made a connection at the RA4 pin of the microcontroller, I have to tell whether there is a rising edge identified or falling edge identified at the RA4 pin of the microcontroller. So if you observe here, the T0SE represents timer 0 source edge select bit. So increment on high to low transition. So high to low transition. So that is like this. And increment on low to high transition. That is this. Okay. So at RA4 pin, if I'm going to identify a falling edge, I have to write T0SE with the value 1. If I'm identifying a rising edge, I have to represent a value 0. Okay, at the RA4 pin, if I am going to see a falling edge, I have to write T0 SE with 1. At the rising edge, if I'm going to identify a rising edge at the RA4 pin, I have to write T0 SE with the value 0. Now tell me, what should I write in my case? Should I be writing a 0 or should I be writing a 1? 1. First of all, do you know which edge am I going to identify if I press the switch? Do you know which edge will be identified at the RA4 pin of your microcontroller? So 1 for high to low transition. The high to low transition is falling edge. Low to high transition is rising edge. So falling edge is 1, rising edge is 0. Okay. You're saying that you are going to identify a falling edge. But I'm not very sure whether it is a falling edge or a rising edge. Yes. So I can say depending on the circuit which is available. And the circuit need not be same as that of your digital keypad. So first I have to know what kind of circuit is available. So I'm going to see here with the help of help and I'm going to click on content. Okay. So I went to help and clicked on content. Okay. So you can scroll down here. Okay. You will get a new page appear. So that is like a sheet which gets opened in your browser. So I'm going to scroll down to the inputs and I'm going to click on push buttons. So here you can see there is push buttons. Now when I click on push buttons, you can observe here how the connection is being made. Now please check with one of the switch and tell me whether there is a rising edge or a falling edge identified. Or you just tell me what kind of circuit is available, whether it is a pull up circuit or pull down circuit. So pull down circuit. So you can see here. So like this, one end of the switch has been connected to the ground like this. Okay. So sorry. I'm sorry. That is 5 volts. Okay. So like this, one end of the switch has been connected to 5 volts like this. Okay. So this is 5 volts or you can consider it as VDD. And the other end via the resistor is been connected to the ground. And one more pin is connected via the resistor to the microcontroller like this. Okay. It's a pull down circuit. Okay. Now, whenever the switch is pressed or whenever the switch is open, what are you going to read at the pin of the microcontroller? Switch is open. Switch is open. What are you going to read at the pin of the microcontroller? Yes, it is 0. And if you press the switch, what will you be reading? If you press the switch, yes. So you are going to read a 1 at the pin of the microcontroller. So whenever I press the switch, which edge gets identified? It's the rising edge. So whenever I press the switch, I'm going to identify a rising edge. So I have to say that I'm going to identify the rising edge. So what should I write to this pin? That is, one second. What should I write to the T0 SE pin in order to represent the rising edge? Yes, I have to write it with the value 0. Okay. So I will write T0 CS with the value of 1 and I'm going to write T0 SE with the value 0. Now there is a timer register. Okay. So that is TMR 0. So initially it is going to have the value 0 return. Now whenever I press the switch, that is your push button, whenever I press the switch, there will be a rising edge identified at the RA4 pin of the microcontroller. So that is when a tick is going to happen. So change from 0 to 1 is going to happen. Again, if I press this switch for another time, one more rising edge gets identified at RA4 pin of the microcontroller. So one more time the tick is going to happen. Now please understand that your timer is configured as a counter. It is going to count the events which is occurring at the RA4 pin of the microcontroller. It is counting the number of events which is occurring at the RA4 pin of the microcontroller. Like this, if I have to get an overflow from 255 to 0, always interrupt gets generated after there is an overflow from 255 to 0. To get an overflow from 255 to 0, tell me how many times I should press the switch? To get an overflow from 255 to 0, yes, I have to press the switch for 256 times. 256 ticks has to happen. So I have to press the switch for 256 times. Now, do you think I have patience of pressing the switch for 256 times? No. So I will load my value, the timer register with 251. Now to get the interrupt generated, how many presses I should do? If I load TMR with 251, I just have to press it for 5 times or 6 times. 51 to 52 once, 53, 54, 55 and an overflow to 0. So I should press the switch for 5 times. Now see the program. I'm going to open a program here. The timer as a counter. So first I'm going to open some of the files here. Yes, I mean, okay. To start with, if you go with the main function, first I have the initialization of the LED. Then I'm doing the initialization of the timer 0. Now coming to the initialization of timer 0, you can see T0CS is returned with the value 1 because I'm going to make use of external clock. Then I'm going to write T0SE with the value 0 because I'm saying that you are going to identify a rising edge. So PSE return with the value 1 as earlier. I'm setting the prescaler to the watchdog timer. TMR 0 return with 251 because I want to get the interrupt generated in just 5 switch press. Then TMR 0 IE return with the value 1, that is to enable the timer 0's interrupt. So it is TMR 0 interrupt enable bit return with the value 1. So after timer 0's initialization, if you come back to the main function, global interrupt enable is returned with the value 1. Then there is init config function. Then I have while of 1. So as of now, nothing is happening. If I press the switch for 5 times, okay, so TMR 0 is loaded with 251. If I press the switch for 5 times, 5 rising edge gets identified at the RA4 pin of the microcontroller. So 5 times the tick is going to happen. Now there will be an overflow from 255 to 0 because of which an interrupt occurs. Now when the interrupt occurs, control comes to the ISR. I'm loading TMR 0 back with 251. I'm toggling an LED and I'm writing TMR 0 IF return with the value 0 back. So I'm just showing you how you can implement timer as a counter. How can you count the events which is happening at the RA4 pin of your microcontroller. So I'm just waiting till the build gets completed. Okay. So build is being successful and loading is completed. Let me load the hex file. So you can keep an eye on both the things. Okay, I'll go to file, then do load hex. Okay, then timer as a counter, distribute, default, production, the hex file. Okay, so please keep an eye on the RD0 pin. After I press the switch for 5 times, you will see an LED getting toggled. Please observe 1, oh sorry, 1, 2, 3, 4, and 5. Can you see the toggling of LED? So LED was 0, it is made 1. Again, I have written TMR 0 with the value 251. Again, if I press the switch for 5 times, you should see the toggling of LED. Observe 1, 2, 3, 4, and 5. So you can see the RD0 has turned off. So again, I press it for 5 times. RD0 is going to get turned on. So like this, 5 event occurs at the RA4 pin of the microcontroller. Then the interrupt is going to get generated. I just wanted to highlight that the tick is going to happen depending on the occurrence of the event at the RA4 pin. So there can either be a falling edge identified or a rising edge identified. So you have to tell which edge will be identified. Accordingly, you are going to increment the value in the timer 0. Understood this? Is that clear? Any doubts? Okay. So this completes the next peripheral, which is nothing but timers. If you want, you can make a note of this. And I'm going to proceed with the next chapter, which is, next peripheral, which is nothing but the clock input output. So before that, you can take a note in 2 minutes. Okay, I hope you're done. Can we proceed? All right, so let us begin with this. So the next important peripheral we are going to discuss from today's class is nothing but clock input output. So let me take you to the next topic. Okay, so that is clock input output. Now, what is this clock input output, or why do we actually need this clock input output? So sometimes what happens is there are certain peripherals which will actually be working according to the clock signals. Okay, so generally what happens is there will be some of the peripherals which are going to work with the clock signals for the sake of maybe synchronous data transmission, or maybe for the sake of like the proper communication between the two peripherals. Now, the peripherals are going to communicate sometimes, as I'm saying, with the help of the clock input output. So there is a need of clock input output for some of the peripherals you have externally connected to your microcontroller, or maybe for some of the peripherals which are already available in your microcontroller. So some of the peripherals may need the clock input output for their operation. Now it is a duty of yours to provide that particular clock input output. Now what happens with this clock signal to be generated is you either can get it generated by your own microcontroller. Okay, so some of the microcontrollers will come with a built-in block. So there will be a particular block which will be generating the clock signal according to the required frequency, or sometimes you may have to generate it at a particular pin of the microcontroller. So maybe you have to evolve with the logic and you have to try generating the clock signal at a particular pin of the microcontroller. And all of this we are doing is for one particular peripheral which is in need of a clock signal. So we have to be generating the clock signal, and after the clock signal is generated, the peripherals may end up taking the action at the edges of the clock or at the levels of the clock. So it completely depends on the peripheral you are dealing with. So they may take the action at the edges of the clock, that is either the rising edge or the falling edge, or they may take the action on the levels of the clock. So either the high level or the low level. So it completely depends on the peripheral you are working with and also the requirements of the system which is being designed. So today we are going to learn one of a variant of clock input output, which is nothing but PWM. Have you heard of this PWM before? See, if yes, what do you think PWM represents? So we are going to learn one of a variant of clock input output, which is nothing but PWM. So yes, PWM represents pulse width modulation. Okay. So here we are going to create one of a variant of a clock input with the help of pulse width modulation. So sometimes PWM is also called as duration modulation also. Okay. So as I said, clock input output, most of the peripheral devices are going to depend on clocking. So controllers have to generate the clock in order to communicate with that particular peripheral. So some of the controller's internal peripherals may also work with the help of some external clock which is provided at a pin of the microcontroller. And the action can either be taken on the edges or at the level. Edges is falling edge or the rising edge. Levels can be either a low level or a high level. So I was talking about PWM, one of a variant of clock input output, which is abbreviated as pulse width modulation. You also can call it as pulse duration modulation. Now let us understand what exactly is this pulse width modulation, and after that we are going to learn how to make use of this pulse width modulation, or how to generate a pulse width modulated waveform. Now let me do one thing. Okay. So what happens in the pulse width modulation is, so whenever you actually need, okay, so whenever you want to generate an analog output for some digital value. So you want to generate an analog output with some digital source. So that is when you are going to need the pulse width modulation. So that is the most commonly preferred solution when it comes to you have to generate an analog output with the help of the digital source. Okay. Now, if you see this pulse width modulation, it has been used in several applications. You see it in telecommunications, you see it in audio applications, you see it in motor controls, and in more other fields. So, pulse width modulation is something we use whenever we want analog output out of a digital input. Now, in order to understand this pulse width modulation, we should know what exactly is a pulse. Okay, so we have to first understand what exactly is a pulse. What do you think a pulse is? What exactly is a pulse? We have already studied it before. Rise and fall. Uh, do we call it as a pulse exactly? Full cycle. Yes, a pulse is nothing but a square wave with 50% duty cycle. So if you are asked to define what exactly is a pulse, so I would say it is a square wave with 50% duty cycle. We already have got a pulse generated. Okay, let me show it here. So this is how a pulse is going to look like. It is a square wave with 50% duty cycle. So that means 50% is the on period, 50% is the off period. For a duration of time, 50% of the time the pulse will be in the high state, and for another 50% of the time the pulse will be in the low state. So that is called as a pulse together. So high state and low state together is called as a pulse. It's a square wave in fact. Now, for certain amount of time the pulse will be in the high state, for certain amount of time the pulse will be in the low state. The time it takes for the high state and low state together, we call it as a period. Okay, so one high level and one low level combining together, we call it as a period. Okay, and this period is going to repeat for multiple times, which we call it as cycle. Okay, so this period is going to repeat for multiple times, so we call it as cycle. So you can see there is one cycle here, there's one more cycle here. So repeated pulses, we call it as cycles. Now, the number of cycles in one amount of time is nothing but frequency. So the measure of a cycle in a given amount of time is nothing but frequency. You can see here there are 10 cycles in 1 second. For every 1 second, you're going to see 10 cycles. So what will be the frequency here? So what do you call the frequency as? If you see 10 cycles for one period, I mean 1 second. So we call it as the frequency being 10 hertz. So if you see 10 cycles In 1 second, the frequency is 10 hertz. So let me repeat again. High and low signal together is called as period. So this is going to occur on a repetitive manner. We call it as cycles technically. The amount of cycles present for a given time is nothing but frequency. So here you can see 10 cycles for every 1 second. So the frequency is 10 hertz. Okay, the frequency is 10 hertz. So that is technically the terminologies associated to the signal. So you understood what exactly is a period, what exactly is a pulse, what is a cycle, and what exactly is a frequency. Any doubt in this? Okay. Now observe some of the pictures I'm going to show ahead of this. So you see this is one pulse with certain width. This is another pulse with more width. This is another pulse with a comparatively lesser width. So I'm showing some of the pictures here. So this is the first picture with certain amount of width. This is the second picture with more width. The third picture with lesser amount of width. Now in all these three pictures I showed, do you see something being maintained constant? Do you see something being maintained constant? Yes. So if you see, the duty cycle is changing, but the period is maintained constant. So if you see the first one, so you see high period is 50%, low period is 50%, but it is for 1 second only. So this one, if you see, high signal is for around 75%, low signal is for around 25%. So that is again for a duration of 1 second. So for every pulse you see, I'm keeping the period constant. So what exactly pulse width modulation says is varying the width of the pulse, keeping the period constant is nothing but pulse width modulation. So if duty cycle is not 50%, can we call it a pulse? Yes. So a square wave ideally is called as a pulse. So with 50% duty cycle is an exact pulse. But whatever is the duty cycle, if it is a square wave, you still can call it as a pulse. Okay. So pulse width modulation means you are going to vary the width of the pulse, keeping the period constant. Okay. So I should be varying the width of the pulse. If you see here, in the first case, this was the width. This is the second case. This is the third case. Everywhere, I'm going to vary the width of the pulse, keeping the period constant. So that is pulse width modulation, varying the width of the pulse, keeping the period constant. Now the question comes is, why exactly should I be doing this? Why should I vary the width of the pulse by keeping the period constant? That is because by varying the width, you are going to control the average power which is being delivered to the load. Okay, so by varying the width of the pulse, you are going to manage the average power which is being delivered to the load. So if you observe here, I have a width of 50%. Okay, so I have a width of 50%. You can see the average power. It is 50% only. The average power I'm giving is 50%. So as I increase the width, the average power being delivered to the load is also increasing. As I decrease the width, the average power delivered will also decrease. Okay, so you can see here, I am going to keep the width as 50%, average power delivered is 50%. I'm increasing the width, average power is going to increase. I decrease the width, average power is going to decrease. So, pulse width modulation is varying the width of the pulse, keeping the period constant in order to manage the average power which is being delivered to the electrical load. But I'm keep on saying something called as duty cycle. What exactly do you think duty cycle is? I'm keep on saying something called as duty cycle. I say 50% duty cycle. I say 70% duty cycle. So what exactly is the duty cycle? Yes. So duty cycle is nothing but the amount of time you are keeping the pulse in the high state. Okay. So high time of a pulse is also referred as duty cycle. Just the high state. Okay. So that is nothing but the duty cycle. So duty cycle is nothing but the measure of time where the signal is maintained high. So you can observe here with 75% duty cycle. So this is 75% duty cycle. Now see, with duty cycle of 0%, the average power delivered is 0. With duty cycle of 12%, the average power delivered is 0.6. With duty cycle of 16%, average power delivered is 0.80. So this way, as I increase the duty cycle, you can observe the average power being delivered to the load is also increasing. At 78% duty cycle, average power is 3.9. At 92% duty cycle, average power is 4.6. At 100% duty cycle, average power is 5 volts. Similarly, as the duty cycle decreases, the average power delivered will also decrease. Duty cycle increases, average power increases. Duty cycle decreases, average power decreases. Now, how to calculate this duty cycle? Okay, so let me write the definition here. Duty cycle is nothing but, in simple words, I will say width of the pulse maintained high. Okay, so width of the pulse maintained high is nothing but duty cycle. So how to calculate the duty cycle is, so there is a formula that is duty cycle, okay, is nothing but pulse width divided by pulse period. Okay, so pulse width divided by pulse period. The width of the pulse is nothing but on period of the pulse. The pulse period is on period plus off period. Okay, so that is nothing but duty cycle, which is represented by D. Okay, so duty cycle represented by D is nothing but T on divided by T on plus T off. Do you remember this formula being already studied in your academics before? Yes. So duty cycle is nothing but T on divided by T on plus T off. If you want it to be in percentage, you can multiply this by 100 in order to get it in percentage. So duty cycle is calculated with the formula T on divided by T on plus T off. Now observe this waveform and tell me how much is the duty cycle. 1 second. Okay. So here it is clearly shown the duty cycle is 50%. So if you see here, the duty cycle is 100%. Similarly here, the duty cycle is 0%. So like this, you can observe how much is the duty cycle in that particular pulse. Okay. Now, I told you that you are going to vary the duty cycle in order to maintain the average power which is being delivered to the load. Okay. So, I have to maintain the average power which is being delivered to the load. So, in order to maintain this average power, I am going to vary the duty cycle. But how to know how much average power is being delivered to the load? So that we have a formula, V out is equal to V max multiplied by duty cycle. Okay. Now let us take a simple example. Observe, this is the waveform. One second. Okay. Now consider this example. Okay. So I have a width of this much, approximately 75%, and another 25% it is the off period. Can you tell me how much is the duty cycle for this waveform? How much is the duty cycle for this waveform? Yes. So first of all, duty cycle is nothing but on period. Out of 1 second, for 0.75 seconds, it is in the on state. For 0.25 seconds, it is in the off state. So 0.75 divided by 0.75 plus 0.25. 1 second. So 0.75 plus 0.25. Okay. So the duty cycle here is 0.75. Now for the duty cycle of 0.75, if you want to find out how much is the average power delivered across the load, assume the maximum voltage is 5 volts. So it is 5 volts multiplied by 0.75. How much is it? It is 3.75. So when you feed an electric load with a pulse of 75% duty cycle, the average power which gets delivered to that particular load will be 3.75 volts. Okay, so maintaining the duty cycle of 75%, the average voltage at that particular pin will be 3.75 volts. Okay, so this voltage, the average voltage is going to vary as the duty cycle is going to change. So that is what I showed here. As the duty cycle increases, the average power delivered across the load is going to increase. If you see, for 50% duty cycle, the average power is 2.5 volts. For 75% duty cycle, average power is 3.7 volts. For 100% duty cycle, average power is 50 volts. So by maintaining a duty cycle of, let's say, 50%, how much will be the average power delivered to that particular load? Yes, it is 2.5 volts. Now, I'm going to give this pulse, okay, whatever I have generated. Assume I'm going to get the signal generated at a particular pin of a microcontroller, and I'm going to give it to an electric load. So for example, let's say I have an LED connected at a particular pin. To that pin, I'm providing this voltage. Okay, to that pin, I'm providing this voltage with 50% of, I'm providing the signal with 50% of duty cycle. Now tell me, do you think to that particular load, I'm providing 2.5 volts of continuous voltage? Am I providing 2.5 volts of continuous voltage to that particular pin? Obviously no. I am actually providing 5 volts for 50% of the time and 0 volts for the other next 50% of the time. Isn't it? So if you consider this example, the unit is not measured here. Okay, observe. So assume the time is in seconds. Okay, so something like this. Assume the time is in seconds. So I am going to give this pulse as an input to the LED. So if you observe, this is a pulse with 50% duty cycle. Now, do you think I'm going to provide 2.5 volts continuously to that electric load? So the answer is no. So I am not providing continuous voltage to that electric load. In fact, I am providing 5 volts for half second, 0 volts for another half second, 5 volts for another half second, 0 volts for another half second. Now, if there is an LED connected, don't you think I will obviously see the toggling of LED for every half a second? So, will I not see the toggling of LED for every half a second? Yes. And can you look at this and tell me how much is the frequency? Can you observe this and tell me how much is the frequency of the pulse? It is 1 hertz. For 1 second, I am generating only one pulse. So the output is so evident that you can easily identify the toggling of the LED. Now, I have to fool this electric load. Okay, I'm not going to provide 2.5 volts of continuous voltage, but I have to fool this load as if I am providing this 2.5 volts of continuous voltage. Okay, I have to fool this load. I cannot provide 2.5 volts continuously. I just have to fool this particular load. Now, how to do that is, observe as of now, for every 1 second you are seeing the toggling of the LED. What if I'm going to give 100 pulses for 1 second? Just assume I'm going to provide 100 pulses for 1 second. Okay. In that case, will you be able to identify 100 times of toggling of the LED? Will you be, for 1 second, do you think our human eyes will be able to identify 100 times of toggling? Obviously, no. Very similar to that, even your electrical load will not be able to identify 100 times of different voltages. So you are switching from 5 volts to 0 volts, 0 volts to 5 volts for 100 times in just 1 second. So in that case, even your electrical load will not be able to identify, and it feels as if there is 2.5 volts being provided on a continuous manner. So that is how you are going to vary the average power which is delivered to the load. So in order to make sure you are controlling the average power which is delivered to an electric load, what should you be doing? In order to deliver an average power to an electric load, what should I do? First, I have to vary the duty cycle. Second, I have to vary it in a higher frequency. So I have to make sure that the device is not able to identify that there is toggling of the LED, like toggling happening. Okay, so that is how your okay, I'm sorry. What if we provide the capacitor to the LED circuit? So it doesn't matter whether you are providing the capacitor or a resistor. So it is just consuming some power. But what is being provided to that electric load feels as if you are providing the continuous voltage. Okay. So that is how the pulse width modulation is actually achieved in order to maintain the average power which is being delivered to that particular load. So with the help of pulse width modulation, if I have to summarize, so pulse width modulation in fact is a technique of varying the average power delivered to the load by varying the duty cycle of a particular pulse. Okay, so I would say pulse width modulation is a technique which is used to generate a pulse in such a way that the load which is being fed with that particular signal is not getting affected. So we just are changing the average voltage which is being delivered to a particular load by varying the width of the pulse. And also, please remember, we are keeping the period constant. Okay, we are going to vary the width of the pulse, keeping the period constant, and that switching will be done on a very faster rate that the load will not be able to detect that particular switching. So that is nothing but pulse width modulation when it comes to the clock input output. Now, if you want a little more power to be delivered to the load, you just have to increase the duty cycle. So you want to decrease the average power delivered to the load, you have to decrease the duty cycle. But the switching has to happen on a faster rate. You cannot take 1 hertz, or you cannot take 2 hertz, 3 hertz. So keep it like 100 hertz, 200 hertz, 300 hertz. So sometimes we have 5 kilohertz, 10 kilohertz and all. So that is how fast the switching is happening, and you will feel as if there is a continuous voltage being delivered. Is there a minimum frequency we should select? It is going to vary from one device to another. So sometimes what happens is how the device is going to interpret, how the device is going to respond. It completely varies. So in case of LED, your like frequency should be generally more than 100 hertz, because LED can interpret things lesser than 100 hertz generally easily. So it is suggested that you keep at least above 100 hertz, so that the device is not able to identify that switching happening between 0 to 1 and 1 to 0. Okay, so that is nothing but pulse width modulation theory. Any doubt in this? Any doubt here? Okay. Now let us proceed. We have to generate our own pulse width modulated waveform. So our idea of coming here was to understand how to generate a clock pulse, how to generate a pulse width modulated waveform. So there are three ways of generating a pulse width modulated waveform. First one is with the help of built-in block. So most of the microcontrollers will come with a built-in block. So they will help you get the pulse width modulated waveform generated of the required frequency and of the required duty cycle. You just have to specify how much is the duty cycle you need and how much is the frequency you need. So accordingly, the pulse width modulated waveform will be generated at a pin of a microcontroller. If the built-in block in the controller is not available, then there is one more way of generating the modulated waveform, that is with the help of timers. So you can see for how much time you want the signal to be in the high state, for how much time you want the signal to be in the low state. So with the help of the timer, you can actually achieve the pulse width modulated waveform. And the third is, if the timer is also not available, assume some microcontrollers will have limited amount of timers and they are already busy doing some other task. So if the timers are not available, then you have to make use of your own logic to have a modulated waveform generated with the help of a super loop, with the help of some logic. We will be able to generate a modulated waveform at the pin of the microcontroller, and that we call it as bit banging. Okay, so that is called as bit banging. So first you can have it generated with the help of the built-in block, you can have it generated with the help of the timer, or you can write your own logic to have a modulated waveform generated at the pin of the microcontroller, and that is something called as bit banging. So there are three ways of generating the pulse width modulated waveform. Can we proceed with the programming part? Okay. So in today's class, let us go with the bit banging way of generating a modulated waveform. So we are going to generate a pulse width modulated waveform with the help of bit banging method. Okay. Now we have to write our own logic to have the modulated waveform generated. So let me start by writing a program. First, I'm going to write a main function. Then inside the main function, I should call the init config function. Okay, so this is the init config function. And I should take a while loop also. So while of 1. Okay, so something like this. Now, what do I want to do inside the while of 1? We will decide. So first, in order to achieve 50% of duty cycle, so I am going to take two variables. One is unsigned, let's say unsigned integer called duty cycle. Okay, so it is duty cycle return with the value 50. Okay, then I will take one more variable called period, return with the value 100. So I'm going to generate a pulse width modulated waveform of 50% duty cycle initially. So duty cycle is 50, period is 100. I will take one more variable called loop counter. So just for the sake of the loop, and I'm going to have it just taken as I don't want to initialize it. Okay, so for period being 100%, 50% is the duty cycle. For a period of 100, for 50 times I should keep it in the on state, and for the rest of the 50 times I have to keep it in the off state. Okay, so I'm not keeping period as exact time, so I'm randomly taking. So period return as 100 and duty cycle return as 50. They are not referring the exact period in seconds or milliseconds. So I'm taking period as 100, out of which for 50% of the time I have to maintain the signal high. So what I'm going to do is I'm going to take a pin of the microcontroller, which is RD0. Okay. So at RD0, I will try generating a modulated waveform. So initially, I will write RD0 with the value, let's say 1. Then after this, for, let's say, loop counter is equal to 0. Then loop counter lesser than duty cycle, and loop counter plus plus. Okay, then I'm making RD0 back to 0. So let's say loop counter, I don't have to do the initialization. Loop counter greater than, let's say, duty cycle, and loop counter plus plus. Please look at this and tell me, will you get a pulse generated of 50% duty cycle if I take it like this? So ideally what I want is a pulse with 50% duty cycle. So something like this, 50% on, 50% off. So 50% on, 50% off. This is what I am ideally expecting. So do you think I am going to get the same with the logic I have written? Please check. Okay. So first observe, RD0 is initially 1. Then how many times is the first for loop running? How many times is the first for loop running? Yes, it is going to run for 50 times. Then I'm going to make RD0 back to 0. How many times is the second loop running? How many times is the second loop running? Check this. How many times is the second loop running? Only one loop needed for 50% duty cycle with bit inversion. That is right. Uh, but what, as of now, for 50% duty cycle, this is fine. What if I will go for 70% duty cycle or 80% duty cycle? Will you be able to do it with a single loop? So that is my idea. So as of now, I'm keeping it as 50%. Okay, I was asking, what about the second for loop? How many times is the second for loop running? After first for loop, uh, loop counter value is now 50. Yes, it is. I guess infinite times. Yes, actually the second for loop is running for infinite number of times. It is not at all ending. So loop counter will be 50 initially. 50 greater than duty cycle will be true for infinite number of times. So 50 you take, 51, 52, 100, 200, whatever you take, it will be greater than duty cycle. So it is going to run for infinite number of times. So what is that change I have to make here? Yes, so I have to write loop counter lesser than period. Okay, so I don't want an and here. Directly I can write loop counter lesser than period. Okay, so now do you think it is going to work for 50% of the times only? I mean, first time if you take RD0 as 1, the loop is running for 50 times. Then you make RD0 as 0. Again, the loop will be running for 50 times. Again, you get back RD0 will be made 1. Loop will be running for 50 times. RD0 will be made 0. Loop will be running for 50 times. Am I not getting a pulse with 50% duty cycle? Don't worry about the period. I randomly have taken 100. Okay. So for certain amount of time, if you see, I have achieved 50% of duty cycle. So this is 50% of on period, 50% of on off period. But do we suggest to keep a for loop in our programs anytime? Is it suggested to keep it? No. So we always have to write a non-blocking statement all the time whenever we are supposed to write any program. So observe how am I going to change it. So if loop counter is let's say lesser than duty cycle, okay. So RD0 will be returned with the value 1. Okay, then I'm going to remove this. So I'll write else if loop counter is is lesser than period, okay, I'm going to write RD0 is equal to 0. So after this, when loop counter reaches 100, I mean period, I have to update it back to 0. So I would say if, okay, if loop counter plus plus is equal to period, okay, then you are going to assign loop counter back to 0. So here also you have to do the initialization. See, if loop counter is lesser than duty cycle, RD0 is returned with 1. If loop counter is lesser than period, RD0 is returned with 0. Loop counter plus plus is equal to period. Loop counter is returned with the value 0. Now observe how this is working. Initially loop counter will be 0. So 0 lesser than duty cycle will be true. RD0 is returned with 1. So then you go with the if block. Loop counter plus plus will be 1. 1 equal to period will be condition false. So you come to the while of 1 again. Loop counter this time will be 1. 1 lesser than duty cycle will be true. So one more time RD0 is assigned with the value 1. So for 50 times RD0 will be assigned with the value 1 like this. Then after the first condition fails, it will go to the second condition, and for 50 times RD0 will be assigned with the value 0. Again for 50 times RD0 will be assigned with 1. For the next 50 times RD0 will be assigned 0. Am I not getting a pulse generated of 50% duty cycle? Yes. And this is the period. Okay, this completely is the period. So for this period, I'm seeing 50% of duty cycle. Okay. Now what we will do is, we will try achieving the same. Okay. So I'm going to see the output on the RD0 pin of the microcontroller. So observe. I'm going to create a new project. Close. Then file, new project. So I'm creating a new project, microchip embedded, standalone, next. So this is mid-range 8-bit MCUs, and this has to be microcontroller, the PIC16F 8778. Then next, the compiler. Then project's name, I'm keeping it as bit banging only. Bit banging. Okay, and I'm clicking on finish. So a project gets created. Meanwhile, I have to add a source file first, a main.c file. So I'm going to give a main.c file created. So going to the source file, new main.c file. So file name is main, extension I'm keeping it as C. Okay. Now, actually, in my program, I'm using RD0 pin. Okay. So RD0 is an LED. As of now, I don't have a oscilloscope to show you the output with 50% duty cycle. So instead, I will feed this to an LED and I will show you how it is happening with 50% duty cycle. Okay. So how to do this? I will go with the basic initialization of the LED first. That I will do it in a header file. So header files, new, and C header file. So header file's name is main, extension is h. I'm creating a main.h file. So it is taking a little time. Okay, fine. So after this, in the header file, let me delete all of this unnecessary thing. So I'm going to take a header inclusion done here. So that xc.h header, I will add it here. Okay. Then I'll define some macros. Ash define LED array as let's say port D, and ash define LED array DDR is nothing but TRISD. Okay. Then I'll take one more macro ash define LED, return with the value RD0. I'll take few more macros. Ash define on as let's say 1 and hash define of as 0. Okay, so I took some macros here, and in the main.h I will include that header. Sorry, in main.c I'll include the header main.h. Are you people able to follow this? Okay. So going with the initialization, first I have to set the direction of LED. So LED array DDR has to be returned with the value 0x00. Then LED array, in order to turn off all the 8 LEDs connected to LED array, what should I write? 0x? Yes, so 00 again. Now coming to the while of 1. Okay, so I'm going to copy the same program as it is. First, some unsigned integer variables taken. I'm pasting it here before while of 1. And these things I'm going to copy as it is. Everywhere it is not RD0, I have given a macro as LED. So I'm going to use that LED. Okay. So that is it. I have written a program with 50%. I am going to generate a pulse with 50% duty cycle. So period is 100, out of which 50% of the time it is on, 50% of the time it is off. Okay. So period is actually, I have kept it as 100. Now, if you observe here, I'm going to build this. Okay. So the project is being built. Okay, so build is successful, loading is done. Let me load the hex file. So under this, bit banging, distribute, default, production, the hex file. So do you see the toggling of LED? Do you see the toggling of LED? No, right? But actually, do you see, delay is not required here. Yes, the LED is glowing with 50% duty cycle. I mean 50% brightness. That is because the input I'm providing at RD0 pin is so fast. I'm providing 1010. See, period is 100. Okay. And this is 50. So for a period of 100, I'm keeping 50. So my signal I'm providing at RD0 is very fast that it is not able to see the toggling. I have to make it a little slow. So let me take the period as 1 lakh and I will make this for 50,000. Okay. And this will be unsigned long integer. Okay. So now observe. I'm going to save and build. Okay. So I'm giving the build main project. Okay, build is suck build failed. Incompatible intermediate code version. 1 second. Okay, so now build is successful. So I'm going to do the file reload last. Can you now see toggling of LED? For 50% of the time it is on, for 50% of the time it is off. Okay, so that is because what I did was earlier, okay, my period was very small, it was 100. Okay, so it hardly takes how much time to get 100 condition check to be done. So it hardly takes, maybe one instruction takes only 200 nanoseconds. Okay. Within 1 second, you are toggling the LED for multiple times, which is why you were not able to observe the output of toggling. So here what happens is, for 50%, sorry, for 50,000 iterations, you are writing LED with the value 1. For another 50,000 iterations, you are writing it with the value 0. Again 50,000 iterations, you are writing it with 1. Again 50,000 iterations, you are writing it with 0. So the period I have taken is large and the frequency I have kept is small. So that is why as of now you are able to see the toggling of LED. But if I reduce the period and increase the frequency, I will not be able to see the toggling of LED, because LED will feel as if there is continuous smaller voltage being provided to it. So that is why LED was glowing with small amount of brightness earlier. Now if I want 75% of the duty cycle, what should I do? If I want 75% of the duty cycle, yes, I just have to make 75,000 here. Okay. So in that case, you will get 75% of duty cycle. See, the period I'm keeping here is not fixed. I don't know whether I'm keeping it as 1 second or 2 second or 3 second. I'm randomly taking a value. For that, I'm fixing the duty cycle, 50% or 100% or 85%, whatever it is. So according to that, if the signal being fed at a pin is having smaller frequency, then you can evidently see the toggling. If it is of larger frequency, you can see that the toggling will not be identified. The load will feel as if there is continuous voltage being provided. Understood this? How can we use breakpoint in this? So it is not possible like adding breakpoints, or we have scope, right, for high frequency. Obviously, yes. So we need high frequency. So just to show you that lower frequency is important for our operation, I just wanted to show that it is glowing with 50% duty cycle. So which is why I'm like showing it like this. So I just wanted to show a pulse. So I cannot show the pulse as I don't have an oscilloscope. So I'm showing it fed to the LED. So in that case, if you observe 50% of on period, 50% of off period, you have to understand that there is 50% of duty cycle being provided. So high frequency, we do have an example to be shown. I'll show you and make you understand it in a better way later. Got it? And somebody was asking for breakpoints. Okay. See, Raja, if you are asking for breakpoints, you can apply it for certain things, but you are not executing your code in the IDE. Your code is being executed in your microcontroller. Now, if you apply some breakpoint, how will you say your microcontroller to go to the next instruction? So we don't have that mechanism to tell the microcontroller to go to the next instruction. So if you want to debug, simulate and all, in that case, you can add this. Okay. You want to see how your code is working, you want to debug, you can use the simulator, you can check. But while it is being executed on the microcontroller, breakpoints are not going to work. Okay. Any other doubts? Okay. So this is one example of how to generate a pulse width modulated waveform with a required duty cycle at a particular pin using our own logic. We call it as bit banging method. So we have two more ways of generating the modulated waveform, that is with the help of built-in blocks and with the help of timer. So doing it with the help of timer is a part of your assignment. We will see how to do it with the help of built-in block. And also there is one more example we are going to try, that I think we will do it in the next class because I will not be able to complete it if I start it now. So there is one more example where we try implementing something called as LED dimmer application with the help of this uh, um, PWM itself. So we will control the average power being delivered to the load with the help of variable duty cycle. So as we increase the duty cycle, the average power delivered to the load will be increasing. As we decrease the duty cycle, the average power delivered to the load will also be decreasing. Using that, we will observe the output on the LED and we will see how exactly is that operating in the next class. Any doubts in this? Okay. So let me tell you that you don't have class tomorrow. So we are going to meet back on Monday. Okay. So the next class will be on Monday, and you are going to understand few more examples on like clock input output, and we will continue with another peripheral, which is nothing but the SSD. Okay, so we are almost close to the peripherals now. So once clock input output is done, we have SSDs, and after that we have CLCDs, then we have matrix keypad and ADC. Four more peripherals we will be done. So by next week we will be done with the peripherals hopefully, and the other next week we will start with the communication protocols. Okay, so we should be done as of now 11 classes are done today, 12th class is done. So another 7 to 8 classes we will be done with peripherals, then 7 to 8 classes we need communication protocols. So like 15 to 17 more classes we will be done with the module. Okay. So please have your attendance mark before quitting the session. Here is your QR. Thanks for attending today's class. We will continue on Monday again. Thank you all.